Welcome to the Explainer. Okay, have you ever actually stopped to think about what's going on under the hood of your machine when you browse the web? Today, we are literally tearing down the engine and looking at the internet right from the perspective of a Linux operating system. We're going to break down the exact journey of a single piece of data, from the very millisecond it leaves your computer to the moment it comes back. I mean, it seems like such a simple action, right? You pull up a bash terminal, you type ping google.com, and boom, instant response. But underneath that incredibly simple command, a massive, highly coordinated sequence of events instantly kicks off. Like, why is it that sometimes your IP address looks completely normal, but you still can't connect to the internet? Or why can you sometimes ping an IP directly, but a website name just absolutely won't load? Well, today, we're going to trace the fascinating chronological journey of a single packet to understand how connectivity truly works, and we're going to answer those exact questions. To really wrap our heads around this, we've got to rely on three absolute pillars of Linux networking. You honestly cannot have a functioning network without these three elements working in perfect harmony. First, think of the IP address as your home address in the digital world. Second, the route table is your road navigation system, or GPS. It tells the data exactly which paths to take. And third, DNS, or domain name system, is your trusty phone book. Keep these in the back of your mind because everything we discuss today builds directly on top of these three simple concepts. All right, so every journey begins at home, right? Before your Linux box can talk to anyone else, it has to figure out its own identity in the network world. By typing the IP address or ifconfig command, Linux basically checks the mirror. It looks at its network interface, usually something like eth0, and finds its assigned identity, say an address like 192.168.1.10. But here is the really interesting part of that address, the CIDR mask. You'll usually see it attached at the end as a /24. That /24 is essentially a boundary marker. It tells Linux exactly how big its local neighborhood is. If your computer wants to talk to another IP address, the very first thing the Linux kernel does is check this mask to ask, hey, is the destination right here in my exact same local neighborhood, or is it somewhere far away? If it's in the same neighborhood, what we call a subnet, the devices can communicate directly without needing a router at all. So what if the destination is actually in that exact same local subnet? Let's say we're trying to reach 192.168.1.20. Linux knows it can skip the router entirely, but there is a catch. In a local Ethernet network, switches don't actually care about IP addresses. They only understand physical hardware addresses, which are known as MAC addresses. To bridge this gap, Linux uses a broadcast protocol called ARP, or Address Resolution Protocol. It basically stands up in the middle of the local neighborhood and shouts, hey, who has the IP 192.168.1.20? Tell me your physical MAC address. The target device replies with its hardware address, and boom, communication can begin. Now, obviously, Linux doesn't want to be that annoying neighbor just shouting over the network constantly. It's incredibly efficient, so it takes notes. It saves these MAC addresses in an ARP cache. By typing the command ipnay in your terminal, you can pull up this exact cache. You're looking directly at the mapping of your local neighborhood, seeing exactly which IP addresses map to which physical hardware addresses right on your network. But wait, what if our packet's destination is completely outside our local subnet? Imagine you want to reach a Google server all the way out at 8.8.8.8. Linux checks that CIDR mask we talked about earlier and immediately realizes, wait a second, this is definitely not in my local neighborhood. When a destination isn't local, shouting with ARP just isn't going to work. The packet needs directions, and this is exactly where the IP route command comes into play, pulling up the routing table. This routing table steps in as the navigation system for your packet. When Linux checks this table, it's hunting for a specific rule on how to handle unknown external destinations, and it finds the default gateway. You'll usually see it listed as something like default via 192.168.1.1. Think of this as the final exit door or the border control to the outside world. Linux is effectively throwing its hands up and saying, look, I have no idea where 8.8.8.8 is, so I'm just handing this packet to my router and letting the router figure out the rest of the journey. Okay, let's put all of this together into a blazing fast 5-step sequence. First up, the kernel builds the actual ping packet, which is an ICMP echo request in plain text. Second, it checks the routing table and realizes it needs to send this to the default gateway. Third, because that gateway is on the local network, Linux uses ARP to find the router's physical MAC address. Fourth, it wraps all of this information, source IP, destination IP, source MAC, and the router's MAC into an Ethernet frame. And finally, step 5, it blasts those electrical or wireless signals right out through your network interface card into the physical world. Okay, plot twist. Up until now, we've only been talking about raw IP numbers, like 8.8.8. But let's be honest, we humans are terrible at remembering numbers, which is exactly why we type google.com into our browsers instead. But since computers only understand numbers, before Linux can do any of the stuff we just talked about, it has to check its local phone book. It does this by reading a specific file called /etc/resolve.conf, which tells the system exactly which DNS server it should use to translate those domain names into numbers. Once Linux knows which DNS server to contact, say Google's own DNS server, it fires off a query. Now, it doesn't send the ping right away. Instead, it sends a lightning-fast UDP query on port 53, directly asking the server, hey, what is the actual IP address for google.com? Only after the DNS server replies with a number, like 142.250.x.x, does Linux actually kick off that 5-step connection process we just went through. And you know, this brings us to a wildly common frustration. Your chat apps are working perfectly fine, but your web browser absolutely refuses to load a page. You try to ping an IP address directly, and it works perfectly, but pinging a website name completely fails. This means your DNS is broken. Your network connection is actually totally fine. You've got the car and the roads are clear, but you've lost the phone book. You have absolutely no destination address to plug into your navigation system. So when the network inevitably goes down, senior engineers, they don't panic, and they definitely don't guess. They follow this exact journey to troubleshoot. Step 1, did I even get an IP address? Step 2, is my default gateway configured? Step 3, can I successfully ping my local router? Step 4, can I ping an external internet IP like 8.8.8.8? And finally, step 5, can my DNS actually resolve a name using a command like nslookup? By stepping through this chronologically, you instantly isolate exactly where the connection is failing. Listen, if you can grasp this basic packet flow, you literally hold the keys to the kingdom. What you've seen today isn't just basic IT trivia. It is the absolute bedrock of modern computing. Because the Linux network system is just so powerful, massive technologies, we're talking cloud infrastructure, Kubernetes, software-defined networking, and cybersecurity, rely entirely on these exact decisions happening perfectly millions of times every single second. So you now know exactly how a packet navigates the digital world. But think about this for a second. Every single time you click a link, this entire journey, checking masks, shouting for hardware addresses, querying phone books, and routing across the globe, happens in a fraction of a millisecond. It's just a breathtaking feat of engineering. But if we know exactly how these packets flow, how do we exert control over them? How do we build walls to stop malicious traffic right in its tracks using the legendary Linux firewall, IP tables? Or what really happens behind the scenes of a TCP three-way handshake? Well, we are going to uncover all of that next time. Until then, keep exploring.